Right, so welcome, a very welcome to the third and final day of the 10th Energy Harvesting Dissemination event, Energy Harvesting 2020. Can everyone hear me all right?
Yes.
Yes.
Perfect.
Yep, sure.
Right. Okay, so today we have two more exciting presentations from two speakers, Paul Egan from 8 Power and Daniel Hoffman from Hahn-Schickard, and then we'll have a panel and audience discussion from our panelists, and it'll be great to hear both from the panelists and also from everyone on what your thoughts are on what the next decade holds for the energy harvesting technologies. And just a bit of background for those of you who are joining us first time today, the Energy Harvesting Network, the Energy Harvesting Network was initially funded 10 years ago at University of Southampton and was funded by EPSRC. Did I just lose something? And the Energy Harvesting Network organizes a dissemination event once a year, and this is the 10th iteration of this dissemination event. In the past, we've had dissemination events at various locations in the UK, and this year, due to the current situation that we're in, this is now an online event for this iteration. And in the past 3 days, going through the agenda, which I'll post a link in the chat box so all of you can have access to this. So the link I just posted in the chat box, this will link to the file that I'm sharing at the moment, including the agenda that we've had for the past 2 days, plus the agenda for today. Now, all sessions are recorded and they will be posted on an online platform after the event. And you're very much encouraged to register as a member, if not yet, in the Energy Harvesting Network website. So and then later on, we'll send out a newsletter update on where the videos will be shared, and also for any future events, you'll be well informed if you're a registered member on the website. And it will be great to hear from you on any feedback that you have for this event, as well as any suggestions for future events. If you can fill in the feedback survey linked here. So if you download the agenda I put in the chat box, you should be able to access that. All right, I think there are more people joining us in the meantime, but I think we can have a start, and hopefully more will find themselves into the room. So our first speaker is, as I mentioned, Paul Egan from 8 Power, who will speak to us about energy harvesting in industrial applications. Paul, can I hand over to you?
Okay. Thank you. Hopefully, in the tradition that has become the norm this year, my first question is, can everybody hear me and see me okay? I think that's something we all kind of got used to over the last little while. So I'm now going to attempt to share my screen. Oops, that's not the one. So let's share an application screen.
Yes.
Which should be. Hold on. Okay, so that's this. With all these things, it did work in the practice session half an hour ago. So let me just get that ready. Okay, share that. Then hopefully now everybody can see my screen there. Good. Or has that gone a bit too wonky? Right. Okay. So my name is Paul Egan, and I'm the CEO of 8 Power. And obviously, we've had quite a long history with energy harvesting, particularly with University of Cambridge. But what I really want to do today is take a little bit of time to go through how we've really changed from, as it says in the title there, from an everlasting battery company to really finding an application that really needs energy harvesting, and then turning that into a business. And in our case, we're now doing condition monitoring of industrial assets such as motors and pumps. So just a little bit about today. So we'll have a little quick catch up on history about how we got to now, and really the evolution from everlasting battery to fit and forget condition monitoring. And it was quite a gradual process actually. We obviously started out as a company with the energy harvesting technology, and for a while we thought we would be providing a component to other people's systems. But it became clear fairly rapidly that when we went to see customers, they say, "Oh, this is great that we don't have to change batteries, but you know, we'd really like to put a sensor in this particular thing. And oh, and while you're there, if you're doing a sensor, could you do any wireless for us?" And given the history of our team, what we've done in wireless networks and mobile handsets, it seemed a pretty logical step really to wrap more of an application around the actual technology itself. I'll talk a little bit about why we think energy harvesting is so important for this next industrial revolution. And we use the 1 milliwatt kind of unit as why that's incredibly important for energy harvesting. We think that the 1 milliwatt, being able to generate 1 milliwatt when an asset is actually active, that has quite big implications for what we can actually do with that. But one thing I will probably open up the discussion at more towards the end, and I'm really keen to get everyone's views on this, is one thing we've discovered. We've been working with ABB over the last couple of years, and it's become apparent that the world is moving from kind of fixed speed motors and pumps and industrial assets to variable frequency drives. So the idea that you can change the speed of a drive to either save power, or if things are process driven, then it gives you the opportunity to possibly save power but also use better assets as well. And there is a whole massive piece of work around a wideband harvester for those types of devices. So this is one of the original slides that was put together, I think, in 2016. So the company was founded out of Cambridge University by Yujia Ashwin-Sesha, Jise Yan, and Kenichi Soga back in 2015. There was some seed funding put in place by IP Group, but the company really came to exist as we know today in 2016 with a seed fund investment. I joined the company in November 2016. And we spent probably the first 18 months or so looking at planes, trains, and automobiles, and wondering, you know, where was the application going to be for this technology. We did a bit of a pivot, I would say, in 2018. We had a change in the structure. I became CEO, and then we really did a kind of ground up analysis really of where we thought the real market for this could be. And again, with input from customers, we realized that machine condition monitoring gives us a nice stable vibration source in terms of operating motors and pumps. We don't tend to have too many extremes of vibration or shock, as we may have seen in things like rail or road or aircraft. So we really thought that's quite a good place to be. And then over time, we managed to find a particular niche, which in our case is in water companies. So they have lots of assets. Many of these motorized assets are actually unmonitored. And it just seems like the kind of place that industry in particular is coming up the industrial curve, and it's now ripe now to have a lot of this digital transformation actually done. Okay, so that's what we look like in 2016, and this is what we look like today. So we have a very different makeup of the leadership team there with myself. I've been engineering is my background and was for the first 28 years of my career, very much in semiconductors, wireless networks, and Internet of Things. I was part of ARM and CSR in the early days of both of those companies, and I co-founded a company about 10 years ago called Newell, and the technology we developed there was acquired by Huawei, and that technology is now being rolled out as narrowband IoT, which is a new cellular standard for Internet of Things. Martin, our VP of Engineering, he's definitely the brains of the organization. He's been around the Cambridge scene for 25 years or something. Sorry, for 35 to 40 years. People know him from Acorn and other things as well. Richard and Glenn, again, they're fairly well-known things there. I would say we're still quite a small company. We're still only, we're less than 10 people, but we think we've managed to achieve quite a lot in that time. So, what are we doing now? So this are a couple of the slides that we present to customers. So we provide what we call fit and forget condition monitoring. So for us, fit and forget really means that we want to do everything. So it's a full stack system. So everything from the sensors at the bottom, through the energy harvesting, through the communications, and everything up to the cloud and the analytics as well. This kind of service will enable customers to move to condition-based maintenance, or CBM as they call it, or some people are using the term predictive maintenance as well. We've got some proven technology in terms of the battery-powered sensors we've done. You know, we're not anti-battery, we're not just energy harvesting, we're all about solving customers' problems, and we'll come on to a little bit about that in the detail at the moment. And at the moment, we're focused on UK water, but this technology and system could be used on virtually any motor or pump or almost any other kind of a rotating machinery. And I think we've definitely moved from the kind of startup phase into the growth phase as well. So we've had some more funding, so I think we're on a trajectory to hopefully start to grow next year when we get out of COVID. So we've tried to, in all ways of kind of corporate world, we've tried to really articulate our value proposition. And it's really this idea that we want to save customers time and money with fit and forget condition monitoring. And this allows customers to really focus on their business, which could be anything. At the moment, it's water, and that could be either water supply or it could be wastewater processing as well. But we really want to improve the availability and reliability and performance of those assets. And with the advent of COVID, it now means that potentially you don't have the opportunity to send staff to site, or you may not have the ability to send staff to site, as we've seen. So we think that those two things actually marry up quite well. So the problem as we see it, this is our kind of problem statement. There's lots of industrial assets out there at the moment. Most of them are unmonitored, and we would say quite a lot of them are actually unloved. Now, in any kind of industrial environment, you would expect there to be a scheduled maintenance regime. And true enough, people can go around once a month, once a quarter. They may do a service check, they may check lubrication, they may check temperatures. But most of the work tends to be kind of visual inspection if it gets done at all. When assets do fail, and it tends to take quite a long time for a lot of these things to fail, certainly our experience, a lot of these problems develop over weeks and months, they don't develop over days and hours. But when assets do fail, it tends to be, oh no, we've got to fix that. It's got to be a reactive maintenance call out, which is expensive. So the idea of reactive or emergency maintenance can range anywhere between 4 and 10 times the cost of a scheduled maintenance job. And also there's the whole thing about you need to get things done. So this idea of unexpected failure has all kinds of knock-on and consequential impacts there. So everything from unplanned downtime, loss of revenue, and particularly in regulated industries, it could mean that the regulator may end up fining you for not delivering a service, or in the case of water, there's potential for pollution incidents or lack of supply. So we think that the solution, bearing in mind that most of our customers are not necessarily experts in vibration analysis, condition monitoring, or even the motors and pumps themselves, we think we have to have this full stack system. And for us, it has to be very low cost, it has to be easy to read, and it has to reduce the risk of things actually going wrong. So we're becoming the experts to actually help people run their assets an awful lot better. So certainly for us, the idea of combining everything into the complete system, so the energy harvesting, which removes the needs for regular battery changes. It also means there's no wiring when we go to install the systems, means that we can fit a lot of these devices to existing assets very, very quickly. And again, we've been doing quite a lot of work with Anglian Water recently, just on this piece. Okay, so anyone that's ever looked at an industrial Internet of Things system will see this is a very traditional system diagram. So we attach our sensors to an asset. In this case, we have that attached to an electric motor. The sensor itself contains a variety of sensors on board, and I've got a slide on that coming up. But effectively, we sample some of the main KPIs. So we sample vibration, temperature, magnetic field. We've got audio on there as well, so we can take short audio clips. That data is then processed locally on the sensor. And we have the option, we can either just send calculated KPI values, or we can actually send raw data. We've chosen Bluetooth 5 as our bearer of choice to actually send data across the network. We have an on-site 4G gateway. Now that does need a permanent power supply, but that only needs a single socket, runs about 15 watts, something like that. So we have looked at the idea of possibly powering that by solar or other renewable energy sources. And one of the other reasons we chose Bluetooth is it means that we can actually interact directly with the sensor from a mobile handset, so a tablet or a phone. That data is then transferred over a cellular connection to our platform, where we can do more analysis, visualization, and actually present data over an API. So we think one of the interesting things here is a lot of our customers have spent quite a lot of money and time investing in some of these platforms. So it's unlikely that our startup is going to replace some of these platforms customers have already got, but we think this incredibly valuable regular data stream is going to augment a lot of the work that's already being done there. So a couple of words on what we've done so far. We were part of the ABB Industrial AI Accelerator last year. And again, it was to validate the energy harvesting sensor and wireless performance. And it was an interesting thing. The phone call came in, it was just before Christmas. And we wouldn't have described ourselves as an AI company, but we took the call because it was ABB and we thought it was interesting. And they said, well, if you can do what you claim you can do and you can solve the problem of powering sensors in the field for long periods at low cost and high performance, then we think this is a game changer in terms of what we can do for analytics. If it's true, then we would like to use your processor and your energy harvesting platform to really start running some of the more complex computational parts, particularly around sensing and algorithmically, to actually do a lot of the AI-based predictive maintenance. So we were part of the program. We graduated successfully from the class of 2019, and we're expecting customer deployments with ABB sometime in the first quarter of next year. In the meantime, we've obviously been pushing on with customer engagements with ourselves, with Anglian, Severn Trent, and Yorkshire Water. And I think by the end of in fact, by the middle of December, we'll have something like 300 of our battery-powered sensors in the field. And the first VEH sensors will be coming out in the first quarter next year. Just a little quick word on analytics. So from this data, we have various views that we show to people. And really, one thing we've discovered is it's in the world of condition monitoring, it's about getting the right data to the right people. So if you were an area manager and you were running maybe a large plant, you might only want to see a set of green boxes that everything's okay for your assets. Maybe if you were in the operations room, you might want to dig down a bit deeper and look at the vibration levels or crest factor or what the temperatures of these particular things you're actually seeing at the moment, so you get a little bit more data there. If you were doing a repair, you might want to start tracking how vibration has changed over time or how maybe temperature is tracking. And again, we've got ways of overlaying multiple bits of data from the different sensors over the top of each other. And then obviously, if you were doing some analysis, you might want to look at a full FFT or the spectrum that we've actually captured from the asset there. So really, we've worked quite hard to make sure that those views are available to the right people at the right time. Okay, and then what do we do with the data? Well, obviously there's, for us in terms of motors and pumps, there are kind of four main things that we're really looking for, of which that would be misalignment between the motor and whatever the motor's driving, imbalance and looseness, but the real killer is bearing faults. So looking at the way that bearing faults develop over time, we have a whole spectrum there that we can start to look at. So for early bearing stage detection, we need to be sampling the accelerometer at around about anywhere between 20 and 60 kilohertz. That gets, because these are small bearings and they rotate very quickly, we need to be operating up there. But as we're discovering, most of our customers are only really interested in this later stage, which is slightly easier processing for us to do. This is really where they take action in the next few weeks or next few months rather than the kind of next few days. So one thing that has made this a lot more complicated is the move to variable frequency drives, and we've got a little slide on that coming up in a second. So at the moment, we've got our ultra-low power sensor stack is running in the field. We use industrial lithium coin cell, and we get somewhere north of 10,000 readings out of this, which would be once an hour for just over a year or so. We've seen these running quite comfortably for 18 months so far. And the sensor includes accelerometer, temperature, humidity, magnetic sensors as well as a microphone. It's got a Cortex-M4 on board, so we can do a lot of the DSP processing actually on the sensor. So this becomes more of an edge device. And with the flash storage, we can store those vibration readings as well. Now, the reason I put this up is this shows you our sensor platform, and in terms of just how low power this particular part is. We're now taking this sensor platform, and we're actually going to be using pretty much exactly the same schematic, the same components in the energy harvesting version of this. And from the numbers we've seen so far, we're pretty confident that this should just be a complex, you should just be able to slot this straight in, but rather than having to rely on battery power, we're going to be able to rely on the energy harvesting for this. And the goal in energy harvesting is obviously the 10 years fit and forget that I mentioned earlier. So why is energy harvesting so important? So people say, why don't you just use batteries? Well, having done the work with ABB and some of the work we've looked at, some of the things we've done with SKF and other companies like that, we know that sensors are only going to get smarter, and the idea that we're going to be running more AI actually on the sensors themselves. Now, more intelligent sensors are going to need more power. And I'm very happy to engage with any software engineers out there, because never in the history of development have they ever said, I'll tell you what, I'm going to take a load of functionality out. You can have a smaller battery and you can need a smaller processor. We just know over time that power is a little bit, and software is a little bit like gas and overdrafts. They expand to occupy the available capacity. Now, there is no Moore's law for batteries in the way we've seen processors develop, but there is Kuhme's law, which said that really for a fixed computing load, sort of per joule, we're expecting to see energy halve every 1.5 years. Well, that mapped pretty well until about 2010, and that 1.5 years has now gone out to about 2.6 years, which means that the actual curve that we're actually seeing is actually starting to slow. So we know that just fitting more bigger batteries won't solve the problem, because a lot of the systems we're looking at, it's actually leakage current is actually one of the main dominant factors that takes power down, rather than actually the processing and running of sensors as well as the wireless piece. And we know that temperature is a really big killer for these things as well. So from where we're sitting, and again, we seem to be validated. There's other people coming out with energy harvesting sensors we see all the time, different technologies. We've seen TEG, we've seen indoor solar, we're seeing other kinds of vibration. Our view is that energy harvesting is a fundamental technology really for the next generation of what we're going to call intelligent industrial sensors. So this is an interesting, really, this is the world that we're occupying at the moment. So if anyone's done any kind of condition monitoring at all, you'll be familiar with the ISO 10816 vibration standard. So this is a standard that really puts different classes of machine into the 4 different categories there. It's a good indication of overall condition, but this will not show you individual failure mechanisms. So we can see, depending upon the size of the machine, the various vibration levels we get will indicate whether the machine is operating, it's in a good state, it's satisfactory, unsatisfactory, or unacceptable. So we would say that good and satisfactory only really needs existing maintenance when we start to detect a problem. Unsatisfactory, you should really start monitoring these assets more regularly and more closely, because there's obviously, you expect degradation over time. But maybe as we get towards the end of life, particularly if we've been tracking run hours, we can see that certain faults will actually start to develop. And obviously, if we're into the unacceptable region, then that means that there is potential for catastrophic failure there. We've picked a band to operate in, which is really the 1.8 millimeters per second, which is the kind of good band. And when we look at the larger machines, particularly sort of class 2 and class 3, which is anything above 75 kilowatts, even most of the brand new machines we've seen installed tend to end up being deployed with the kind of 1.2, 1.8 millimeters per second. It's just a factor of how these things go in. Even when they've been laser aligned and they've done all the mounting points and things like that, we still see just a small amount of vibration, which in our case is great, because that's still enough to actually generate power. But the good news for us is that the more the machine degrades, then potentially the more the vibration increases, which means there's more opportunity for us to harvest more energy in the VEH, which means that we can then start to run the sensors more often, and we can actually run some adaptive sensing, which means as we have more power budget available, we can do more processing and report more often. Okay, so why is 1 milliwatt so important? Why don't you just use a battery? So all the work we've done so far, both in the field and in the lab, says that if you have a asset that is generating about 1 milliwatt from the VEH, that is on a 50% duty cycle, that is enough to keep all the sensors reporting data every hour, and it keeps the battery full. Now, it also means that we've put some protection in there, which means we can also operate against the full industrial temperature range, because we know that as we go below 40 degrees, then charging batteries and capacity of battery drops off. But as we get to the higher temperatures, so it's not just the leakage of the batteries, but it's also the leakage of the electronics that starts to dominate in terms of power consumption there. So really, we've got this, we've kind of sandbagged this 1 milliwatt level that we want to get. It seems to play quite well with the customers we have, because a lot of the assets we see do tend to operate for probably, I'd say probably anywhere between 50 and 70% of their time. So certainly, I mean, we've also got assets that run 24/7 as well. So why don't we just use lithium thionyl chloride batteries that can deliver loads and loads of power? Well, you know, D cell at 90 amp hours, 3.6 volts, that's somewhere in the region of kind of 60 watt hours. But you have to remember that when you look across the temperature range, that may be the room temperature characteristics of those cells, but the reality of actually getting these things into the field, and also the amount of current that you can draw from these batteries at any one time, is usually limited to a few tens of milliamps. So if you were running a cellular system, you'd have to design a pretty sophisticated power supply system to be able to draw the large currents needed for the instantaneous transmissions. The other thing for us as well is lithium. You know, it's a rare earth metal. There are environmental impacts of actually mining lithium. We're also going to be in competition with electric vehicles for at least the next decade or so. So we think that lithium is if we can find a way of avoiding using lithium, then we really should do that for that. And again, there's the cost and end of life of those cells as well. So looking at narrowband performance we've got so far of our existing energy harvester, we've been running some long-term tests, and we've also been running some on a sort of bench shaker system, where we've been running at 100% duty cycle, and we've been doing in-band and out-of-band generation there, and we've been running the sensors. I think that's every half an hour or maybe every hour in that first band. But about 4 weeks ago, we've now put the same energy harvesting sensor onto our demo system, and this was the system that we built for the ABB project last year. And we can see that the green line here is the voltage of the battery, and over time we can see that we're actually increasing. So it's a little bit like as long as we're generating more than we're spending every day, then we're in a good place. And effectively what we do in the morning is, when whoever is first into the lab switches the system on, and we run it for 6, 7, 8 hours a day, and then it gets switched off overnight. So you can see that for this, we're on about 25% duty cycle. And if we're sampling data every 2 hours or so, that's a pretty good indication that we're in that kind of 1 milliwatt, 50% duty cycle. And again, these are the kind of levels of power that we need to be able to deliver to say that if you deploy this on an asset at this kind of vibration level, then we know we can deliver these kind of insights at that time. So the challenge for us is going really from this kind of narrowband, can be quite high power vibration energy harvesting, to what we're going to do on variable frequency drives. The work with us with ABB last year showed us that the world is moving from fixed speed to variable frequency drives, and there's a whole bunch of reasons for that. In terms of actually, if you look at the way that pumps operate, there's some data around these affinity laws that if you can drop the rotation speed of the pump but still move the same amount of water, then you can get quite a large energy saving. So what we're starting to see now is people using VFDs at a fixed point, but allows them to actually benefit from that large energy saving. But then we've got some process-driven industries where we can see the speed of the motors vary from anything from 50% of their designated rotor speed, anything up to 120%. Now, at the other end of the scale, we've got some customers who will under-specify a motor for their pump, and then they will choose to ride it above the maximum. So they save money on the cost of the pump, but potentially they're actually using more money in terms of energy. But there's a whole different thoughts around the economics of that there. We're seeing standard motor speeds anywhere between 40 and 80 RPM and 3000 RPM. So we need to make sure that we should have a wider band that we can actually generate energy from to be able to run the sensors and run all the wireless and reporting. So VH in this VFD environment is tricky, but it is the way forward. So here's a couple of idealized or an idealized view of our world. Our early modeling would suggest that if we could get 10 hertz of bandwidth at even fairly modest vibrations, then we should be able to generate enough power to report probably 2, maybe 6 times a day, something like that. And if you imagine that that green band is really in the green band here, and if the machine is operating in a fairly good, is in fairly good order, there doesn't seem a great deal of point in just sending lots and lots of the same kinds of data all the time. Obviously, as the asset degrades, then we will hopefully start to generate more power, which means we can either start reporting more often, or potentially we could actually do more processing on the data we've actually got, or maybe run the sensors in a different way. The opportunity to run slightly different algorithms for processing it obviously comes into effect there. And obviously, as we get into these other areas here, when we get into the unsatisfactory, then we're comfortably into the reporting every hour and having more than enough power to spare as well. So for us, the idea of trying to get to 10 hertz across a wide bandwidth and generate that kind of power, that is the challenge that we're facing at the moment. We've got some ideas, but we don't have anything to show about that just yet. Okay, so the conclusions that we see at the moment is that vibration energy harvesting for industrial Internet of Things is a real opportunity, and potentially it could be massive. So the idea of actually having a sensor that you deploy that's completely wireless and maintenance free, that doesn't require battery changes for 10 years, that is where we're seeing a lot of people aiming for that kind of functionality at the moment. The work we're seeing with ABB, it's convinced us that the world is moving to VFDs. So that means that the next generation of vibration energy harvesting, it's going to have to support much wider bandwidths. It's going to have to probably higher power as well, because the moment we start doing more with the software, then that's going to mean we're going to have to run the processor probably more often. And despite the fact we're getting lower power processors with each generation of silicon, all the software will probably make up for that. So there seems to be this kind of fixed number around about the 1 milliwatt generation that seems to solve that. And obviously these things have got to be robust and reliable. Again, some of these sites we're going to, they can operate lights out for many weeks or many months, and the chances of actually having to send someone is quite rare. So what we're really after is a robust process. There's a robust harvester that can generate power over a large bandwidth, and we can actually use that for the sensing we've got. And that, I think, is me.
Thank you very much, Paul. And now we're open for questions. If anyone has any questions for Paul. Yeah, Alex.
Yeah, thank you very much. A very interesting talk. I was just wondering whether vibration energy harvesting is the best type of harvester to use in this application. I know that motors often run quite hot, and it seems you've got a lot of challenges associated with variable frequency motors. So are you, as a company, tied to vibration energy harvesting, or would you be more agnostic about the type of harvester you would use in these applications?
I would say, given the fact that you know we're not anti-bat, we're really about trying to solve customers' problems. So again, there are a number of choices that we would have for energy harvesting. I think probably one of the reasons we've gone for VEH is that with a sort of compact unit. In fact, if I might have my camera on, so if I stop sharing that and get my camera on the go. So we've got effectively, just to give you a kind of order of scale of where we're at the moment. So that's our coin cell based sensor, and that's really the energy harvesting based version. So it's about kind of twice the size of a D cell. In terms of ease of fitment, being able to bolt that onto some of the existing places on a motor or a pump at the moment makes it very simple. Thermal energy, it's interesting. We haven't seen anything that's really quite that easy to fit yet that can give us the kind of milliwatt type power levels. If there's some things out there, I mean, certainly we'd be interested in having a look at them. But again, I say we're not because we support batteries as well as harvesting. I wouldn't rule anything out at this stage.
Thank you. Paul, I think there's a question for you in the chat box.
Okay. Let me have a quick look at that. So, the chat box has just disappeared. Hold on. Okay, no, I've lost the chat box. Where's that gone?
It's in the bottom right.
Bottom right. Hang on. Right. Okay, got this. Hello, Paul. Thank you very much for the interesting presentation. What is the sampling frequency of the product when it's applied for monitoring? How long, how often does the data collection support Bluetooth 5 to support energy consumption? How much energy should be harvested? So we sample data every hour, and the accelerometer that we've got at the moment has 4 kilohertz bandwidth, so we get a kind of 2 kilohertz sample across the band there. We take an 8-second sample for rotating assets currently, but that would be based on a kind of either a 1480 or 3000 RPM asset. We're looking at different collection times for different assets. We've got some very slow rotating assets that rotate about somewhere between half a hertz and 1 hertz. So we're actually looking at actually extending that sampling period as well. Bluetooth 5 is super low energy, and for a vibration recording, it's several hundred kilobytes. So we'd be looking at anywhere, depending upon the radio link budget between the sensor and the gateway, we could be looking at anywhere from a few seconds, maybe up to kind of 30, 40 seconds to actually transmit that as well. And again, we think that the idea that the 1 milliwatt power generation should give us comfortably sampling, processing and reporting that data once an hour. We've got some choices in the system. We don't always have to send the raw data. Potentially we could do the processing at the edge and then just send the values and the FFT. That can actually cut down the amount of data that we send. So potentially some customers are only actually after that.
Thank you, Paul. I think there's another question on before.
Right. Oh yeah, great talk. Many emerging applications for vibration millimeter. Oh, okay. So let's talk about MEMS. Now, I know that the original academic founders did quite a lot of MEMS when they were at the university, and it's something I'm very keen to look at. Given that I've got a semiconductor background, I do find that quite a really interesting area to look at. It's worth saying that obviously in the kind of MEMS scale, that potentially we would have orders of magnitude lower power. However, being able to package a completely self-powered sensor into a kind of centimeter cube type footprint would enable us to put sensors in places we can't even put wires at the moment, and particularly the benefits of being able to operate at higher temperatures. We revisit this on a fairly regular basis, and our thinking currently is that if we were to do a MEMS energy harvesting play at that kind of small scale, it would require significant investment. And the number that when customers ask us, or sorry, when investors ask us about what are you doing in MEMS, we've always said that we think it's probably a 15-man team for about 3 years and probably a $10 million investment just to get us to a working prototype. So if we look at the supply chain we would need obviously MEMS manufacturing partner. There's a lot of work needs to go into packaging. There's a whole bunch of things around the tools required to actually design these things, fabrication tools, EDA tools, simulation, process development, performance. It would be almost like starting another semiconductor company if you wanted to do it, if you were serious about doing it for some of those large scale applications. Currently, we're not funded to do that, but we have got some IP in the MEMS space, and it is very, very interesting. Now, I would say that maybe in a couple of years' time, after we've hopefully made some progress in where we are with the macro scale devices, I think that will be the next horizon we should be looking at. And again, I think the idea of having self-powered sensors that can fit into almost things like kind of hand power tools and kind of consumer devices, that definitely feels quite exciting.
Thank you very much, Paul, and thanks everyone for the questions. I think we just mindful of time, it'll be good to move on to the next. Thank you again, Paul, very much.
Okay.
And our next speaker is Daniel Daniel, are you ready?
Yes, I'm ready for presentation. I will
Thank
share
you.
my. So now you should see the screen in a couple of seconds. I welcome you all to the last talk of this session and also to the last talk of this conference. My name is Daniel Hoffman, and I have been working on kinetic energy harvesting systems at Hahn-Schickard for a couple of years. And today I would like to give you an overview about our research on adaptive energy harvesting systems. First of all, I would like to share some experiences that we have made over the last years. I think primary batteries are almost always in competition with energy harvesting. Of course, batteries are small, they have high energy densities, they are cheap to get. So here the problem is that environmental energy is often not reliable. We have large fluctuations. Sometimes it's unpredictable. And in many cases, we have only small amounts of power available. So an energy harvesting system must have some benefit, and that benefit has to be elaborated for each application. And a third thing is that the energy consumption of sensor actor systems, the energy consumption is mostly not steady, so it changes over time. And from our customers, they already came with sensor systems, and the energy consumption was often too large. So we had the problem to really develop an energy harvesting system that can provide this energy consumption. So, but there are opportunities by careful design considerations. So one important thing is the co-design of energy harvesting. So that the co-design means of the three components, that's the energy converter, the power management, and the sensor system. It is very important to minimize the energy consumption where possible. So this can be done by intelligent mode of operation, for example, or by a careful choice of system components. And you should really use energy-driven strategies such as adaptive sampling, adaptive clocking. And we also made the experience that firmware optimization has a great role on energy consumption of the complete sensor system. So all these points should be taken into account when designing energy harvesting systems for specific applications. Well, from our perspective, we have always faced a major application, which is the self-sufficient condition monitoring of things. We have already heard it in the last talk. So things can be technical assets like gearboxes, pumps, electric motors, tunnel drilling machines, etc. So there's a lot of technical equipment outside which needs condition monitoring. And things can also be human beings, for example, or animals, as we have seen yesterday. So, and the solution for self-sufficient condition monitoring would be to have embedded, intelligent, self-sufficient, and wireless sensor systems. I think this is not new. That's why just one slide about the applications. So in this talk, I will focus more on the technology side of tunable harvesting systems rather than on the applications. So I have here two slides to recall the basics of vibration harvesting. As everyone knows, usually a mass spring system is used to couple vibrations to an electrical damper. And by having this system, we have a resonant system. And that brings me to the characteristics of such a system, which is summarized here. So a mass spring mass system has a fixed eigenfrequency, which is determined by the stiffness of the system and the mass of the system. We get a quite narrow bandwidth for such a system. The maximum power is achieved at resonance, only. So if the excitation frequency mismatches the resonance frequency, the power drops down significantly. And such a system can be tailored for a specific application, but it is not able to adapt to a changing frequency. So when we have this changing excitation frequency, we would like to have a system that can adapt to that changing frequency. And that's why we have worked on tunable harvesting systems in the past. So the reason why we need the ability to adapt to the excitation frequency becomes clear when we look at technical vibration sources. So we have investigated a number of vibration sources in different projects in the past. For example, compactor systems, electrical drives, vibration tables, gearboxes in cars or in ships, and also general pumps and electrical motors. And from that, we found that the dominant frequencies are in a certain range, to be found in a certain range. So this range is roughly between 10 and 100 hertz, depending on the technical environment. So we get bandwidths from 25 hertz up to 80, 130 hertz. Of course, in the engine compartment of a car, you also find higher frequencies, higher dominant frequencies. And of course, there are a lot more of technical environments that you can investigate for these dominant frequencies. From this investigation, we have defined some kind of target specification. So we wanted to develop a tunable harvesting system that can tune between 20 and 80 hertz, which gives a bandwidth of 60 hertz. So let us now look at frequency adaptable systems. In this talk, I will focus on mechanical tuning techniques. Of course, there are also other techniques like electrical techniques to tune or to change the eigenfrequency of a mechanical system. Looking at mechanical techniques, we can use external forces to change the eigenfrequency of a cantilever-based structure. These external forces can be axial forces, tensile forces, or compressive forces. We can use radial forces to change the system stiffness. We can use a movable mass to change the momentum in the system. And this, by doing this, we also change the eigenfrequency of the cantilever system. And we can vary the geometry of the cantilever. So when looking at the basic equations of a cantilever beam, we can find out that we have several options to change the geometry. That would be the length of the cantilever, the height of the cantilever, the width, and the shape of the cantilever. And yeah, a great challenge follows from that is the implementation. So in theory, it's quite easy to identify the different principles and to do calculations and simulations, but it's really a challenge to do the implementation. So here's a slide showing some state-of-the-art. As you can see from this table, there are a lot of research groups working on tunable harvesting systems. So a number of groups use axial forces to change the eigenfrequency, but other groups also use radial forces, or they change the length of the cantilever. Also, movable mass has been presented, and also some kind of internal stress change in a piezoelectric cantilever. The big problem is that all the proof of concept devices, they are so different, and the boundary conditions which has been used are very different. So direct comparison of the different tunings is quite difficult. And it's not possible to conclude which strategy is best for a certain application. That's why we have worked on different frequency adaptation mechanisms at Hahn-Schickard. So we have worked or looked at changing the geometry, which is the length and width. We have looked at systems where we change the shape of a cantilever by bending a single beam or by using a tense double beam. And we also looked at external forces, in particular at axial forces, as you can see from the right sketches here. So then let's start with the first one, which is variation of the length of a cantilever. On this slide, you see the concept. So we have a movable anchor, which is moved by a threaded spindle with a stepper motor. And this movable anchor can then clamp the cantilever at a certain position. So we get a certain effective length of the cantilever, and we can move it from some maximum point to some minimum point. So that's the side view. Here we see the top view, and we have here our magnetic circuit, so the energy converter, and in the gap between the magnets, a coil. So we did some simulations first to identify the expectable frequency range. In this case, we used a U-shaped spring, and as you can see, also from this equation here, due to the L to the power of 3 characteristics, we get a quite large frequency range, which depends on the thickness of the spring, obviously, of 30 to 100 hertz, when we have a range of from 5 millimeters to 30 millimeters, a movable range. Yeah. Here in this slide, you see the implementation of this device. We have used a U-shaped spring element with 0.5 millimeter thickness. Here you see the threaded spindle, the stepper motor. We have a displacement range of 5 to 30 millimeters, and the displacement per motor step is 1 millimeter, and the energy consumption per hertz is 196 millijoule for this particular device. Here we can the results. We achieved a bandwidth of just 23 hertz from 24 to 47 hertz. The voltage of 4.5 volts corresponds roughly to 9 milliwatt at 2200 ohm, which is the optimum resistance, and 2 millimeter per second squared as the excitation. There's some kind of problem when you look at this movable anchor. So there's some discrepancy between both. So it's contradictable because on the one side, we want the anchor to be movable so that we can move it. On the other side, we want the anchor to firmly clamp the beam. So on the one side, we would have so when we have a firm clamping, we have high friction. If we have a good movable anchor, we have a looseness of the spring. So this is the one reason why we get a much lower frequency bandwidth than calculated. And another drawback is that the voltage and power declines strongly with frequency. Declines strongly with frequency. We assume that this has to do with the compromise we have to make between a movable anchor, which needs to be movable, but on the other side, it needs to firmly clamp the beam. For varying the width of a cantilever, we came up with this concept. So we use a comp structure with unlockable beams. So here we see the comp structure. At the free end, we have some kind of mass and the energy converter. We have the outer beams are permanently clamped to keep the spring in position, and the internal beams can be temporarily clamped, can be locked or unlocked. And the nice thing about this concept is that we can combine the different beams in such a way that we get, if we all have all loosened, we have the minimum eigenfrequency. If we have all clamped, we have the maximum eigenfrequency, and we can have all combinations in between. And the big advantage is that we can, for example, jump from one frequency, F2, to frequency F6, just by clamping one other beam. So we don't need to make many motor steps to achieve a larger tuning range, but we can use very effectively the concept of the combinations of these spring elements. Of course, the combinations, they increase with n, so 2 to the power of n. The design can be, or the system can be tailored or designed to a specific application. Here we see an implementation of the device. Here we used a comp structure with a total width of 100 millimeters. It contains 6 unlockable beams, and we used bistable lift magnets. So we only need energy to change the state from locked to unlocked. And when it's locked or unlocked, we don't need any additional energy. Here are the results. The bandwidth we achieved was 28 Hertz from 15 to 34 Hertz, 43 Hertz. So that's the experimental result. Of course, in simulation, we predicted some higher bandwidth. Here we have some similar problems, that a firm clamping of the beam is difficult because the actuator doesn't have this force to clamp it as when you screw it down. One drawback is that we need a large structure to accommodate the different beams elements. We also need more than one actuator to clamp each beam separately. But the energy required for clamping one beam is quite little, so we need 50 millijoule per actuation. So that's quite good actually. And the power and voltage is shown here. It also declines with frequency. So when we get to higher stiffness, of the system, to higher frequencies, the power and voltage drops. Here we can see our third concept regarding the change of geometry. When we look again at this simple equation, we have the second moment of area in this equation. So we can change that by changing the length, changing the width or height, as we have seen previously. But we can also change the second moment of area by moving area elements in the direction of the y-axis. So this is can be done by bending the beam. So when we have a curvature of the cantilever beam, then we can change the second moment of area. And in the design, it's shown how we do it. So we have here the spring element, and we have here a motor and a gear mechanism, and we can use pull wires to bend the spring element. So the expectable frequency range, we just didn't know what to expect. Well, we knew that there should be a large frequency range possible because the moment of error changes quickly when you bend a beam. So here you see the implementation of the device. We used a 60 by 40 by 0.4 millimeter spring element. You see here the energy converter. You see the stepper motor with gear, and you see the pull wires. Here's a side view where you can see the spring element with some curvature. The energy consumption per hertz is here 192 millijoule, and the results are shown here. we were really excited to see the results. We can achieve a quite high bandwidth. Here in this case, in this particular case, from 36 to 78 Hertz, and more is possible. And we see that we have a quite large plateau, power plateau, where the power doesn't change so much. So it doesn't decline continuously, but it keeps on a certain level. Of course, we see here some decline, which we can't explain at the moment. So it is that we need to find the reason why we get this slope as shown here. Of course, there are some drawbacks. We need a large spring, a spring which is so large that you can the bending without exceeding the stress limits of the material. The forces for bending the spring increase quickly. And so that means we need a quite big stepper motor, which has the sufficient force to do that. Here's the next concept, which is the TENS double beam or double cantilever. We found this concept by chance somehow, but it turned out to be quite interesting. The concept works as following. We have two parallel double cantilevers. Here we have attached a mass or our energy converters or a magnetic circuit. We have some initial gap between the two spring elements and the anchor. So one is fixed, one is movable. And when we pull this up, we increase here the distance d. But this distance is fixed due to the mass. And tuning happens then by varying the distance d. We did first some simulations to estimate the expected frequency bandwidth, and we found out that the frequency bandwidth that can be achieved is quite high, and it also depends on the initial gap between the two. So for a large distance DO or D0, we get some smaller bandwidth, and the smaller the gap gets, the steeper is the curve progression. So for 1 millimeter initial gap, we get more than 100 Hertz of bandwidth. From here, 65 up to, I don't know, for 300 Hertz in theory. So this is simulation. So because it was so interesting, we built a first proof of concept device with a cantilever of 25 by 24 by 0.3 millimeters. We chose a gap of 3.2 millimeters here between the two springs, and we used just Baser blocks to set the distance d. So there's no actuator involved in this experiment. And what we could see that we are quite we could prove the simulation result. So we get really a large gap bandwidth also in experimental the experiment from over 100 Hertz, from 30 to 135. And the beautiful thing is that we only need small displacements. So just by changing the distance d by 1 millimeter, we can already change the eigenfrequency from 75 Hertz up to 120 here from 75 up to 105 Hertz, which is quite a lot. And also in the other direction, we have a good steepness of the curve. But of course, there are also drawbacks, which you see on the next slide. The power decreases strongly with frequency. So the stiffness gets increases quite quickly when increasing the distance d, and this has an effect on the vibration characteristic. So the power drops dramatically. Actually, this is the big drawback of this principle. And also forces for bending increase quickly. So the more you bend or the more you increase the distance d, the more force you need. And the implementation with an actuator might be challenging. So we haven't done this yet. So we need to look at different concepts, how to do it. Now our last concept, which is the application of axial forces. Here we have focused on realizing the forces by two permanent magnets. So we use a coupling magnet at the end of the cantilever beam. We have a circular tuning magnet, and by rotating this magnet, that's the top view, we can apply repulsive forces and attractive forces. So that gives us the opportunity to apply tensile and compressive strain to the cantilever beam, which increases the overall bandwidth, the tunable bandwidth. So the expected frequency range is about 20 to 50 Hertz for this particular concept and design. Here we see an implementation of this design. Again, a similar cantilever structure, 25 by 24 millimeters with a thickness of 0.7 millimeters. We have here the energy converter, which is almost the same as in all other experiments. So it supports the comparison later on. We have a very small stepper motor on top here. We have no gearing mechanism. Here's the circular tuning magnet. And we have some additional magnet here to compensate any moments. And we need 100 millijoule per step for the stepper motor. Here you can see just a moment, a video. Here the system is off resonance, then we get some rotation of the magnet, and then the system gets into resonance. And so we can effectively convert vibration into electrical energy. Here we see some results for the bandwidth. We achieved here for the system 20 Hertz of bandwidth, from 30 to 50 Hertz about. We can tailor the system to applications very easily by varying the gap between the tuning magnet and the coupling magnet. So if you have a small gap of 4 millimeters or even 3, we can increase the bandwidth, the tuning bandwidth. And by chain thickness of the spring, for example, we can change the center frequency. So we can shift this to higher frequencies or lower frequencies. One should know that if the gap between the tuning magnet and the coupling magnet is too small, we get a bistable configuration. And for this frequency adaptive system, this bistable configuration should be avoided. And another positive aspect is that the output power, output or voltage, is more or less constant over the tuning range. There are a couple of publications I would like to point out because there is much more detail in it regarding this, what I have shown here, the axial force frequency tuning. We have demonstrated a self-adaptive energy harvesting system here in materials and structures. And a colleague of mine at Bayreuth University, he has picked up this research work and made some theory for energy optimized operation. It's a very interesting paper. And he also showed a self-adaptive and self-sufficient energy harvesting system, which was published this year in Sensors. So please have a look in there because time is already running up. I can't show all the results we have here. So with that, I come to my conclusions. Here I have made a table for comparison of the tuning techniques. Here you see the different concepts. And we'll just look at 3 parameters: the bandwidth, the power characteristic, and the implementation. And regarding our target specification, the change of the length does not give us a reasonable result. So we just have 23 Hertz of bandwidth. Of course, we can increase that bandwidth by optimizing the geometry and by design. But still we have the fact that the power decreases strongly with the frequency. Maybe this has to do with the movable anchor, which is here problematic in this case, which I have explained previously. Yeah, changing the width gives a higher bandwidth, but still the power decreases with frequency. We need a large COM structure. We need more than one actuator, and the firm clamping is still problematic. Yeah, bending the cantilever beam has led to a very large bandwidth, which can even be increased by the design of the system. We have a large plateau with constant power output, but still we need some larger cantilever to realize the bending on the picture. So that makes the device larger, and we need large forces to do the complete bending. Yeah, the double beam gives the greatest bandwidth, which is still improvable by design, but here the power decreases strongly with the frequency, which is actually a drawback, a big broad drawback. We just need small displacements, which is really nice, and forces increase quickly as well. But I think this can be handled by the right combination of motor and gearing mechanism. And the axial force principle gives also a smaller bandwidth, which is a drawback, but we have almost constant power output over the complete frequency range. We need small forces because we use moment compensation, and implementation and customization is quite easy. So last conclusion regarding vibration harvesting. Yeah, resonance, it's both a blessing and a curse. There are solutions for broadening the bandwidth, such as nonlinear systems, which we have seen in the previous talk, where parametric resonance is used. We can use adaptive systems, but there's still research work necessary to get a really a system that can be used on real systems, on pumps or whatever. Yeah, some take-home messages or questions when designing frequency adaptive systems. We have to think how often needs to be adapted. So that depends on the vibration source. We need to think how much energy is available for the frequency tuning. So this is dependent on the vibration source, the energy harvesting system, and the consumer. Yeah, how much time is needed to harvest the energy required for one tuning event. That should be considered. And how much energy is required for frequency tuning. So that's basically dependent on the characteristic of the tuning mechanism. And all these considerations should be done when designing frequency tunable vibration systems. So that's it. Thank you very much for your attention. I hope it was some kind of interesting for you. I'm looking forward for your questions.
Thank you very much, Daniel. And the floor is now open for questions. And I already see there is a question in the chat box for you, Daniel.
Yeah, I have here the first question from Hayden Thompson. Interesting ideas, each with advantages and disadvantages. If you were to down select from the concepts, which one would you choose to take forward considering your potential applications? We have, at the moment, we have a project which is about condition monitoring of water pumps for bathing equipment. So in big swimming centers, which are closed at the moment, unfortunately, there are a number of pumps required. And we have a company that is building these pumps and selling these pumps, and they want to include a condition monitoring system. In this project, we are going forward with the axial forces concept, because we have quite a lot of experience with this concept. The implementation is quite easy, and the bandwidth that is realizable with that concept is enough for this application. I hope this answers your question. Of course, it's not easy when you go back to this slide. I'm not sure if that's possible. Yeah, you can see it here. Actually, a combination of this one and this one would be nice. So having a large bandwidth with some advantages in terms of the implementation. It depends on the application, I would say. But we will.
Thank you. Alex?
Hi, yeah, so I found that presentation really interesting, thank you. I was just wanting a bit more information about the axial force tuning technique. Do you have to keep the stepper motor permanently powered in order to avoid it rotating back to another position?
No, because we work with some moment compensation. So we have a second magnet behind the tuning magnet, which compensates any mechanical moments in the system. So the cocking torque of the stepper motor is sufficient to keep the actual position.
I see. Thank you.
Any other quick questions? All right. I think there is one more question.
Yeah, how do you know to what new frequency you should adapt? How do you drive the actuator? I think this can be nicely seen in the publications we have done. I can explain it shortly. The excitation frequency can either be determined by an additional sensor, acceleration sensor, but we used actually the voltage generated by the harvester to determine the actual or the current excitation frequency. Then we had some algorithm to change to the right angle that gives you the new resonance frequency. So easily spoken, you have a lookup table in your microcontroller, which says if you want to adapt to 50 Hertz, you need to position the magnet to a certain angle, which is maybe 45 degrees or so. So that's not difficult.
Thank you very much. Thank you, Daniel, for the talk. Really, really interesting. Just mindful of time, I think we should move on to the panel discussion now, and maybe we can carry forward some of the discussions we're having here to the panel and audience discussion session. Thank you, Daniel, once again.
All right. Yeah, you're welcome.
All right. So now we're going to have our last session for our conference. And I'd like to introduce to you once again some of those who you've already heard from. Matthias from Lightricity from yesterday. You've heard his presentation. Alex and Paul. Alex from the first day you've heard his presentation, and Paul from earlier, and Simon Yarwood from the KTN. And if I may asking each of you, maybe in the order of the panelists named here, if each of you would like to say for a few minutes to voice your opinion on what the coming decade holds for energy harvesting technologies, and then we can open the wider discussion across the panels and the audience. Thank you.
Okay, so it
Simon,
looks like,
would you like to start?
Yep, looks like I'm up first, and hopefully you can hear me. So first of all,
yes.
I'd like to tip my hat to Paul Egan, who basically stole everything I was going to say this morning. So thanks very much for that one. I'm from, as Paul and you and lots of others know, I'm from from KTN, formerly full name Knowledge Transfer Network, but now call ourselves KTN. And I know nothing about how energy harvesting actually works. That's why I talk to loads of interesting people like this group here, the people that work within the Energy Harvesting Special Interest Group, and I go to lots of events. And what I understand is where people are going to utilize energy harvesting. And the thing I was going to say this morning is, I'm not sure what the harvested development is going to be. I'm seeing some technology pieces like, the growth in perovskite and large scale printing of harvesters for PV onto glass, and vibration harvesters as trends, and looking at things like I would say next generation, probably not the right phrase, but future versions of piezoelectrics, so piezoceramics, the sort of stuff that Ionics are doing in the UK. So better at high temperature, no lead and other toxic chemicals in them. But the thing I wanted to say was, and this is the bit that Paul stumbled across, was the need for energy harvesting in the next 10 years is the thing that I'm really interested in. So at the moment, I'm working with Department for Culture, Media and Sport in the UK government, and with Innovate UK, supporting several projects and funding programs about IoT, and looking at digital security within those systems, because often they're not as secure as we'd like to think they are, or as secure as they should be. And a way of doing that often is with embedded intelligence at the edge. Now, again, this was the thing Paul was saying this morning, that the power profile requirements are just going to increase and increase. And things like DSBD, Digital Secure by Design, which is an Innovate UK funding stream under the Industrial Strategy Challenge Fund for business, is going to be pushing more and more requirements for embedded AI and intelligence at the edge and edge processing. And the power profile of what's required is going to go up and up and up. So really, I can't talk about what the harvesters are going to do, but I can definitely talk about what the harvesters are going to need to achieve. And that is delivery in harsh environments more and more. So there's finally seeing more traction with the manufacturing sector. I found it really interesting on day one, where we had the talk from Honeywell about their sudden explosion of interest from customers with their gas sensors. But harsh environments in either harsh temperatures or the nuclear environment, for example, are going to be looking at the demands of these things, and they're going to want to have lots of processing happening at the edge to be able to push packets through onto the network. So really, that's my main takeout from this is, whatever you're going to do, it needs to be thinking about not a small sensor that sits dormantly, just taking the odd reading like we might have in some current gas sensors, but we're going to be looking at more compute happening at a larger scale. And I'll stop there.
Thank you very much, Simon. Alex, would you like to?
Yeah, okay. So I think that the big picture is probably we're going to see a continued prevalence of photovoltaics as the preferred method of energy harvesting, just because it's so simple. You can easily see where light is available, and even where there isn't a great deal of light, you've still got enough power to provide sufficient energy to most types of sensors that are only operating on a 1% duty cycle or below. I think that over the past decade we've seen a move towards applications. So I know that Perpetuum have found their niche in the rail industry. 8Power seem to be taking a similar path. So I think particularly for vibration energy harvesting, we're going to see this continue to be tailored towards applications, and really it needs the harvester producer to be the application provider as well. So yeah, if you're selling your widget, you need the customers to be able to use it. And I think there's also a bigger question about how we can assist users to make best use of energy harvesting technology. So the question of how much energy is available in the environment or in my intended deployment situation is quite a difficult one to answer. And I think there's a lot of work we could do in helping people to select appropriate energy harvesting solutions. Looking to the future, I think we could see an increased interest in sustainability of energy harvesting solutions, considering the embodied energy in the production of these devices, and also what happens at the end of their lifetime, looking at recyclability. Also considering long lifetime systems, how we cope with degradation, in particular of the energy storage devices. batteries and supercaps do degrade, and they degrade a lot more quickly in hostile environments. So I think we need to consider that a bit more carefully. We're also seeing some emerging technologies in areas such as computational RFID. Research are starting to look into that as part of their TRIFID project. Tied in with that, we're looking at intermittent computing. Trying to do without the storage device on an energy harvesting device, and just allowing it to work when energy is available, and to sort of save its state and stay in hibernation until the next burst of energy comes along. That's been enabled by recent developments in low power memory technologies. And I think we're also going to see some developments in fabrics and printable electronics. At Southampton, we're doing some work in printable photovoltaics, printable supercapacitors. So that's suitable for wearable devices as well as other applications where you may want to print electronic systems onto a surface. So in summary, I think we probably want to focus on tools and applications in the future, but we've got a lot of exciting other things happening as well.
Thank you, Alex. And Matthias from Lightricity, would you like to share your opinion about energy harvesting in the coming decade?
Sure. Sorry, I'm just trying to get my video going. Right. Okay. Yes. Yeah. So some really good points there from the previous panelists already. So maybe from my perspective, so looking back, so energy harvesting in terms of wider mass market applications that I suppose sort of most familiar to consumers from solar watches and the calculators, which are, I guess, are sort of great examples in that they're sort of very simple and everyone understands them, and so you pull them out, they always work, and so the benefit is really obvious. And then over the last 10 years or so, we've also seen the emergence of I guess of high value specialized applications for energy harvesting, and to really make a difference or enable applications or use cases that weren't quite possible before with battery powered sensors. So again, so seen some good examples during the course of this a conference, whether that's in gas sensing, for example, or industrial IoT and so on. And so I think we'll sort of see more and more of those in sort of higher value sort of specialized applications as I think the market opens up, and also I think the sort of infrastructure sort of becomes available to sort of plug in sensors more readily and more easily. I think so some very good examples there from 8Power in the talk this morning of how that can be achieved. So I think it's definitely more in that direction that was very likely to see in the coming years. And I suppose the question is whether there'll be other sort of real sort of mass market consumer applications that are being created. And I think there's certainly good opportunities in the sense that we're sort of still seeing very strong progress, not just on the energy harvesters themselves, but also on the sort of entire, I suppose, electronics ecosystem around that. So whether that's a sensor power consumption, the progress on microcontroller level architecture and power consumption, I think that Alex was referring to. And so I think that sort of will able more to be done on energy harvesting nodes than was possible until recently. And so I think so there may be sort of additional sort of maybe sort of more mass market applications, both in industry, sort of asset tracking, obviously is one that's frequently mentioned, or infrastructure monitoring, maybe building automation, where it's sort of likely to be much more widely used. And I guess then there's the question whether sort of really big sort of consumer markets will be accessible, like hearables, for example. Obviously, many people using hearable devices, so true wireless headphones, for example. So the question is can energy harvesting break into one of these markets? I mean, so conceptually, it's sort of, I suppose, easy to see how an energy harvesting device could be making a difference to a hearable, but will the sort of system architecture and all the components be there really to be competing with the sort of rechargeable battery solutions? So I think that's yet to be seen, but I think the opportunities are certainly there.
Thank you very much. Paul?
Okay. So hopefully I'm kind of back online. Yeah, so so sorry for stealing your thunder there, Simon. So there's a couple of things that have just listening to the panel there. If I apply a bit of rear view mirror look into this, and if I look back over my career for the last sort of 35 years or something, so time at ARM, time at CSR, doing the thing at Newell, there was the kind of universal truth of kind of technology adoption is that it always takes longer than you think and it always costs more. And then really truly revolutionary technology, if you think there's a market size or you think there'll be a penetration or there'll be a certain deployment, if it's truly revolutionary, it's bigger than anybody could ever have predicted. But the one that always throws me is whatever you think the target application for a new technology is going to be, the killer app usually turns out to be something that you didn't think of. And again, we've got examples of this of kind of over the years, everyone thought that 3G was going to be for video calls. In the end, it was looking at kind of cat videos. But the one thing that we've come across at the moment, and I don't know if this is just because it's just so new, all the customers we're talking to don't care about energy harvesting. What they care about is how the system that we're deploying is used for them in terms of what it means for availability of equipment. But they're more interested in, do I have to run wires to this, and do I ever have to go back and change the batteries? How the energy harvesting is done within that system, nobody cares. It's only really the system integrators that care. And that's where we can then have this kind of second and third level discussion about, well, how much energy have you got? If you've got that power budget, what processor can you use? And what wireless is available? How much data can you send? But the majority of users really don't care about how that stuff actually works. And I think that was true in probably my time at ARM and CSR. People just wanted a Bluetooth headset. They didn't care what processor was used. They didn't care how the code was written. They didn't care how the radio modulated its signals. They just wanted that end product. And I think we're probably going to go through this as well at the moment as well. It feels like we are at the start of this journey. But certainly one of the things I've been seeing recently is, I'd say probably two years ago, it felt like we were a bit of a lone voice there saying there's going to be energy harvesting industrial sensors, of which we've seen Perpetuum and Everactive and other guys that have been in the market for a long time. But it really felt this idea of trying to get a kind of mass market product out there. It felt slightly alone. I'm feeling a little bit more crowded now than it was, because it must be a good idea because enough people have announced intentions to launch products, or people are trialing products. So I think it's a great thing. But don't rush to invest in any of this stuff yet. I think it's going to be the 10-year journey. But at the end of that 10-year journey, I think we are going to see the adoption of a MEMS technology, because I think just getting the amount of power down and the volume needed to the really massively kind of applications of, again, things probably in wearables, probably things in hand tools, things in tracking, all those kind of things. I think they're going to come with the advent of a truly kind of scalable MEMS, particularly the low cost side, and very much the kind of small form factor. I think industry is going to lead the way for the next kind of 5 years or so, because obviously we know the benefits of getting data from your assets means you can run your operations more efficiently. You can run a lot more lights out kind of operations. So I'd say the future is definitely bright. But whereas 3 or 4 years ago, it felt like it was never going to happen. Now it feels like it's going to be happening in the next probably 2 or 3 years, I would say.
Thank you very much, Paul. And I think now we can open the discussion to the entire conference. And if anyone or any of the panelists or any of the participants would like to share your further thoughts and opinions, or if you have any questions for the panelists, please feel free. Anyone have any comments or any of your own opinions on what you think the future opportunities and challenges hold for energy harvesting technology? So,
okay, so I'd like to ask the other panelists then. So obviously we're focused on tracking condition of industrial assets such as electric motors and pumps. Are there any other, if you were to look at a different kind of application, where do you think that there might be kind of commercial interest? And again, the reason I ask that question is the commercial interest and the size of the market tends to drive the development in some of these places. So if we weren't going to do motors and pumps, where do you think we should be looking?
Shall I sort of start there maybe? So, well, I guess also there's a lot of interest that I guess at least that we're seeing in wearable devices, just because sort of they're becoming, I guess, or have been becoming more and more popular. Whether that's just consumer wearables, or medical wearables, or and so on, I guess that becoming more powerful, so more sensors fitted to them, more wireless, maybe better displays. So I think there are opportunities there. Obviously, it can be very cost sensitive. So sort of having the sort of right technology, offering the right benefit is sort of really important there. But I think that that continues to be one. I think where energy harvesting sort of can make a difference, and I guess so many players in that market already understand. Obviously know what solar powered watches are and so how it might work, and I guess they're also sort of tend to be good at ultra low power design, so they know how to, or are better placed to take an energy harvesting device and do something with it. So if you go into other industries, they might be, I guess, enamored, or they might like the idea of having an autonomous device, but they don't really know how to integrate it necessarily, or what actually to do with it if you give them an energy harvester. So yeah, so that's certainly one. I think I think then as it becomes much more, I guess, diverse. Yes, so there's asset tracking applications, so battery-powered sensors already sort of used and more widely used. I think where there's certainly the possibilities there, and the same in sort of infrastructure monitoring and building automation. Again, I think where we've well, building automation, obviously, if you look at the consumer side, actually, there's been sort of an explosion of sort of consumer smart devices, whether that's home security or entertainment or sort of voice assistants. So I think that's trickier because, yeah, I think energy harvesting obviously can bring something to that to those markets, but we haven't so seen that many people adopt it actually properly or widely. So that I think that remains to be seen. But the market, I guess, is there. For some of the other industrial ones, perhaps it's a bit more obvious asset tracking because it's generally in industry or commercial end users are easier to understand these sort of commercial or longer term cost of operation benefits more readily, I guess, than consumers.
I think I'd agree with that. I think a lot of the applications for energy harvesting are actually quite boring, knowing where things are, knowing what things are doing. We probably don't need to generate massive amounts of power for that. I think the 1 milliwatt figure is probably rather high for a lot of those applications.
I would say, based on what customers and companies I talk to are looking for, it is either the things that keep moving and you're not sure where they ever are, or the flip side is the things that never move and you want to know what they're doing. And I think what do we call it? PEMD, power electronics, machines and drives. So it's a large part of what you're doing already, Paul, with the motors example I saw when I came and saw you in Cambridge a while back. But I think the power electronics, the monitoring of machines and drives is getting more and more with the rise of autonomous systems, autonomous vehicles, I should say, sorry, and wanting to monitor those continuously, but remove any additional drain on the main battery system for the car because of the whole range anxiety piece. So when I was talking to part of the HVM catapult about this from the automotive perspective, there was a lot of keenness for, if I could just monitor the tire pressure in here and how that particular motor's doing on that wheel, but I can't give you any power from my main battery. But then, of course, they're like, but you can't add a really big heavy thing in because it's going to reduce my range again. Yeah. So they do want their cake and eating it, definitely.
Yeah. So you get nothing for nothing. So it's a question of either you either add mass or draw power. You can you can't get away with either, with not having either.
Definitely.
I suppose one
I have a question for the panelists.
I was going to say about the asset tracking thing. If you, because that throws up another question then about what do you do if something is truly remote and is moving. There's the great question about which wireless do you choose, or how do you architect a system to actually use the lowest amount of power to actually transmit its position. And again, that's going to come down to the business case about either how immediate do you need to know of a change in position, or how much are you prepared to pay for that knowledge, and how quickly do you need it? And the obvious thoughts would be there. If we look at the example of somebody like Tile that uses Bluetooth Low Energy tags to put on things, and the fact is they rely on a network being there already and actually using someone else's network as opposed to having a network connection yourself. And I think that's an interesting kind of architectural discussion to have on the kind of asset tracking thing. That how can you build a reliable network when you don't know if a network's going to be there?
I think
you can hear a pin drop right now.
I mean, I guess also there are sort of developments there that I guess that are sort of possibly I guess interesting or exciting. So there's Amazon obviously with its Sidewalk initiative, which is at least in the US is adding LoRa transceivers to the Echo devices that are being sold. And I guess so there's providing another sort of longer range, ultra low power network option. That sort of could sort of help on the consumer side. I guess then similar to, as you mentioned, obviously BLE is widely available on smartphones, enabling Tile to offer their sort of tags there. On the industrial side, I guess it depends. It probably tends to be, if anything, more Wi-Fi or LTE. So which sort of can be a bit challenging in terms of power consumption. So you really have to look quite closely what's feasible there in terms of wireless connectivity.
I think it comes down, with the people I've spoken to, it comes down to you have to hang your hat on something. I haven't come across anyone yet that's bet the farm and lost, which is a good thing, I suppose. Well, not because of their spectrum anyway. There's probably been other reasons, but not because of their communication. When I say spectrum, not because of their communication choice. I was really interested reading about. I've been a bit late to this, a bit late to the story, but reading about Trifid the other day, and I thought that was really interesting. With the approach being, well, you're going to use it in a situation where there will be ubiquitous coverage because we'll put receivers within, I think it was 10 meters, they said the max range or whatever it was. And so the answer is, well, you're only ever going to use it in these scenarios. So we'll make sure in those scenarios, there's the coverage you need. But I suppose your point is they're flipping it back, where if you don't know where it's going to be used when it's out in the wilds, what are your options? There's an interesting point in the chat here, a comment saying there's a lot of activity on swarm satellites to provide coverage to remote areas. But it's a question back to the panel, because I'm rusty. Isn't there then the issue that takes a lot more energy to communicate for that? So again, it becomes the point you're making, Paul, of you can have power or you can have one or the other. It's that triangle. And I think satellite will be even more energy demanding, but it will give you the coverage. And you've got to ask, what are you actually monitoring for? Is it theft? So you need to know the second it moves, or is it just it's going to be delivered to my front door or to the factory door in an hour's time? Different scenarios.
Yeah, so NB-IoT is also interesting, but so that's built on 4G and 5G communication networks, but it has a high energy cost of doing transmissions, so it's a trade-off. How often do you need to transmit, and how big does your storage device have to be to give you the energy you need for that? I think it's probably fair to say that NB-IoT hasn't really taken off. If you look at, I think it's Vodafone in the UK that offers it. There's very little information on it on their website.
I did have someone saying to me recently, well, of course 5G will solve everything. And it was a case of, have you looked at the power needs? Yeah, but that's fun. Definitely fun conversation.
I mean, I think this question, that's why we've chosen the architecture that we have. So we've gone for Bluetooth 5 in the sensors, which is incredibly low power. but it also comes with the potential for meshing if you need to extend coverage, but then it also comes with the coded PHY that's it's a low data, let's say low data rate. It can go down to 125 kilobits a second, but you can get kind of kilometer range line of sight. Now, we wouldn't have any kind of assets reporting in at that kind of range, but we would make use of that extra link budget in some of the industrial environments we've got. Again, we've seen some incredible performance in some of these really noisy machine halls. And when I mean noisy, I mean kind of electrically noisy rather than necessarily just the kind of audio side of it. And again, for us, the hybrid is that we will then report that back to the gateway, and then we use a mains-powered 4G gateway to do the backhaul for things like that. And even that's been interesting. We've had a couple of sites we've had to shop around for network operators and have to use quite large external areas in places to get coverage, just because we end up shipping quite a lot of data. I think to the other point that there are right. I think we're spoilt for choice when it comes to low power, wide area solutions now. So we've got LoRa, we've got Sigfox. I think that takes care of the kind of license exempt band, and we do have LTE-M and NB-IoT if you want to go down the route of licensed or kind of cellular supported. Each come with their own benefits and each come with their own problems. Obviously, there's subscription for anything from a cellular operator, but then you have duty cycle restrictions on anything being in the license exempt band, which limits the amount of data you can send. But if you're sending values, if you're sending a 32-bit number once a day or some small payload, then there's no reason to suspect that you wouldn't be able to use Sigfox or LoRa. Again, other downside there is you don't have a lot of downlink, so it's fine if you've got something that's just sending data up. If you've got something that's more bi-directional, then again, you might want to look at kind of other opportunities. But again, as we say, if you want something super low cost, super low power, that is a fairly sleepy device, then I think there are opportunities out there for using those networks.
All right, thank you. I have one question for the panelists and maybe also for all the participants, because I know there are many seasoned veterans in this field in the participants list as well. Energy harvesting is definitely not a new field. It's been around for some time now. I'm just wondering, what's your opinion on what has been the biggest sort of the limiting factor so far that has, in terms of its mass market uptake or commercialization, or if this challenge has slowly been addressed moving forward?
Oh, I think there's a very simple answer to that. I think the availability of fairly low-cost lithium thionyl chloride batteries, with all of their restrictions and their temperature limitations, but the fact is you've got quite a large energy density in a battery, makes people think, well, energy harvesting is a great idea, but I think I'll just put a battery in this thing and I might get 2 years or 3 years out of it. But that might not be my problem when the batteries need to be changed at that time.
I think I'd agree with that. So I think this is also tied in with developments in applications. So I think in the sectors that we see as being most suitable for energy harvesting, so up to now these sectors tended to be quite conservative. And I know things have moved quite quickly in the past few months for obvious reasons, but I think there was no big driver for remote monitoring previously, if you already had engineers in the field visiting machinery regularly.
I think the Honeywell presentation from day one summed up the entire thing for me. I asked the question, I said, what do you think's driven them to finally realise the thing we as a community have been saying for years? Come on, don't send a chap out on a truck, have a remote monitoring system. And the answer from Honeywell was, well, there's been this pandemic, and that's all it's taken is a pandemic, and for people to realise putting people together on trucks, going out and checking things. And of course, what they didn't say, and what I'm making an assumption here, is businesses are going to be impacted negatively financially. So the figures the presenter was saying on a case of, well, by implementing this at this cost, there are millions of pounds of savings directly attributable. Not even like we've moved things in an Excel. No, this is absolute. You put this in, it will save you this much money, returns within a year. people are looking for that right now, and I think it's really driven it home, and people are like, maybe this isn't such a bad idea after all. But it is quite telling that it's taken this long. As an outsider, I'm looking at the edge of these industries going, this seems like a really sensible idea. Why can't people see that? And I spoke to 60 to 80 people from around the UK community when doing the SIG stuff, and everyone was like, yep, great opportunity, we can do this. Can't find the customers, or can't find customers willing, because it was a change in behavior.
Hi, Nancy. You've a few comments in the chat box. Would you like to unmute and share some of your opinions?
Okay, so yeah, I'm Hayden Thompson. I run a company called Think, and we've been doing sort of various energy harvesting applications for many, many years now. And we have lots of challenges. We actually produce various products. We've put them out in the field, and quite often we go to doing demonstrators for various companies of the technologies. We go to the demonstrator phase, and then it comes to the next phase, which is actually the mass rollout of these things. And then it gets a bit tricky, because it's all of these questions about what's the cost of these devices or whatever. And so in the agriculture sector, for instance, we've done big deployments in Australia, funnily enough, and there we find that the farmers are very interested in the technologies, but they're not really prepared to pay for them. And then you find that you need to start looking at where is the real business case, and the business case is actually linking up with fertilizer companies who are providing the fertilizers to these people. So it's not so much the energy harvesting devices themselves, it's actually providing a service to someone, a whole business service. And so we find that actually the money's to be made on the data. And this is why we actually got into satellite technologies in the first place. Is we realized that we were working in very remote areas, and so we realized that actually the way to make money out of this was actually to control the data and actually get some of the money back for the transfer of the data. And so now we're actually moving into swarm satellite technologies. So we have link ups with new things which are going on in the States, which is looking at providing this coverage all around the world. So we're sort of interested in particularly remote applications, because of course 5G and all these other things will never get to these remote applications. And the majority of the things we're looking at are remote areas where people can't get to. And so this is exactly the sort of customer you're looking for, the people who've got assets in the middle of nowhere, like Honeywell we're talking about the other day, where it costs a fortune to get someone out there to actually get data. So why can't we actually put something out there which is cheap and reliable? And I think it is a difficult thing to sell to people, but actually for a company, it's difficult to make money out of these technologies, because really you need to provide the service, you need to scale up and work with the data as well. And the larger companies can do that, but many of the companies in the energy harvesting sector are very much SMEs. And so they really need to partner with other companies to provide solutions. And I think that's the thing we found over the years.
Very interesting point. Yeah, Roy?
Roy Freeland, Perpetuum. This is a little bit anecdotal, but it's a sort of suitable story for towards the end of the conference. One of the key problems we encountered was salesmen. Let me explain. Salesmen for, say, process industry companies tend to be rewarded as a percentage of the sales contracts they get. The great advantage of energy harvesting powered instrumentation is that it can be fitted by someone pretty unskilled. I've done installations personally in gas plants, and at virtually no cost and effort. Walk in, get the magnet out, stick it on the device, walk out again. It takes longer to get trained on the emergencies in that situation. So why won't the salesman sell it? Because of their commission. If a wireless energy harvesting powered system costs 1/3, which is not untypical of the cost of a fully wired system, the salesman commission drops to 30% of where it would have been, 33%. That's why the salesman isn't going to push it. And I can tell you, having talked to salesmen of process industry companies some years ago, that was their number one concern, was that the value of their contracts would drop. How you get over that, you've got to find champions in the end user customer. But get round the salesman is the problem. It isn't the problem in most products, but it is here.
Thank you, Roy. Very interesting point. Are there any other comments from anyone? All right. Then I think, being mindful of time, we should start wrapping this session up. And really, thank you very much to all the panelists, all the presenters, and all our participants who've attended the conference today and also the past 2 days. Really, thank you very much. And once again, if you can be kind enough to fill out the feedback survey on the performance we've done this time, but also any suggestions that you may have for our next event, that'll be really appreciated. So really thank you once again to all our contributors and all attendees for making this event successful, and some really interesting ideas that were shared and discussed here. Thank you all very much.
Great. Okay, thanks everybody.
Thank you, all presenters and panelists. Thank you.
Thank you.
All right.
Thank you, everyone. Bye-bye.
Thanks, everyone. Have a good weekend.